subcategory of all possible exponential mixed Hodge structure. Then the only information is if you forget about this Hodge structure or the Hodge module, the locally constant, the basic part is just controlled by monodromic and zero. Okay, so notice that say before that when if you have this finite monodromic object, if this if it's already constant when you retreat to Gn, that is when n equal to 0 to 1, then this is just really corresponding to classical mixed Hodge structure. So this corresponds classical mixed Hodge structure. Okay, where you consider this if you have a Hodge structure, then you can consider this Hodge structure supported at origin. Then you consider this I put forward this edge, and then you do this projection. Okay, this will give you an embedding from classical mixed Hodge. Okay, so where this I is from 0 origin to A1. Okay. So you just put your constant constant Hodge structure on Gn and then extend by 0 across the origin. Okay, this gives an embedding of the classical ones to these exponential ones. Okay. So the goal of this talk and the talk in the afternoon of is that we want to say that if we consider finite monodromic ones, actually we can extend this classical motivic consideration for Hodge structure to this finite monodromic set in a quite precise way. And the upshot is that in this setting, if you want to, if you are willing to regard special values of gamma function and Gauss sums as a known object, then this exponential, finite monodromic ones is just like the classical ones twisted by the so-called gamma motifs. Okay, so I will introduce soon.
Excuse me.
Yes.
So is it easy to say what this condition will be for the I guess for MHS of the form of the left board? So if you take some regular function x and then you take the push forward, maybe you take the product with e, so you'll get some exponential mixed Hodge structure, right?
I guess A1, yes.
So is it easy to say what this finite monodromic condition tells about x and f?
Yeah, I always say this example. Okay. This is not always true if you start from an arbitrary function. Yeah, but so this is our typical prototype of example. So if our x is just a1 times u, and then fx, the function, it looks like s. So this is s to the power n times g to the power 2 to u. Okay. So and I want to regard this in this setting as like ramified Fourier transform. So you change this x to the power n. So why is that? So let's see. So if I want to study this exponential twist shift s to the power n times g, and then also we can look at this diagram. So I want to change this to just a variable to the power n. So how to do that? So we have a map u to a1. This is g, and then I want to take this g to be another function to the power m. So we do the base change by this power map, and then this is u prime. So this is Cartesian product, and we have u prime. And somehow this shift you can regard it as just a direct summand to this exponential by S times G prime to the power n. So this notation means that so if this is pi mean. So if you take this pull back and then push forward by this finite map, then this one, then there's a direct summand, which is this one. Otherwise, you have this answer with Kummer shift. So if you want to study this cohomology, for example, the round cohomology, you can as well study this the round cohomology for this one. Okay, but then this is just so somehow exponential to the power s to the power n. So why is that? So you just do the change of variable. You have this a1 times u, a1 times u, and then so here you have the coordinates as u, and then you just change your coordinates to s times u if g is nowhere vanished. Okay, so if g is never 0, then this is just give you isomorphism. So if you have a function on this side, which is s to the power n times u, this is just the same as the function here with the function s to the power n. Okay. And if it's not, there's some zero locus of this g, then you just decompose your space into two parts, the zero locus of g and then the nowhere vanishing part. Then there's a small difference you need to modify a little bit, but anyway, let me just say it this way. Okay. So somehow, if you are in this situation, so somehow actually after this small modification and then change your variable, you just need to consider the exponential function on here, exponential to the s to the power n on here, and there's nothing here. Okay. So what's really essential is just this part on A1. Okay, and so also in this category exponential mixed structure, we have so somehow you reduce your case to this one. So you just push for your constant shift, and this is just so you have constant ones, and then otherwise you have the two more ones. So this is it corresponds to E plus n to R. So from this consideration, we then have R x as we call n times g. It's just compose this into this one. It's x r minus 1 u. Okay, so after this, so if you are in this situation, there's no clear vanishing. Okay, it turns out that if you push forward your structure shift on this one by the function like this, it turns out that it decomposes in this way. Okay, so there's a constant part times the Kummer shift. Or in the round setting, so if you consider R, the round cohomology of this x, this one, and this will be the direct sum of H1 of A1 times the exponential t times r minus 1 u. Okay. So okay, so actually this is the motif I want to this talk is that we want to use another more classical approach to this finite monodromic ones, and then consider this. You use the more Canadian consideration. This is the so actually, you see that because the definition for this finite monodromic one is that you have this existence of this m. So you pull back, this is a constant on this the upper space. But actually, there's a monodromy action here. So which means the essential information is that you need to consider mixed Hodge structure or mixed Hodge module on A1 with a finite group action. Okay, so we have adapted this point of view, and then let me define how this finite monodromic Hodge structure in a more classical term. So let's consider R is either Q or real numbers inside complex numbers. Okay, let me define what is the finite monodromic real Hodge structure. This is consists of V is a vector space or a free modular. R. Vector space and the Q or R. Finite type, finite dimensional. Okay, so with the Hodge decomposition, so very similar to the classical setting. Position C Q A. Okay, but what's different with this classical setting is that now the filtration has index in Q. Such that still you have a complex communication, so PQ conjugate is E2P. And the most important one is that you have a monodromy action. Action I denote this by T, which is defined to be potential of minus pi I T times identity Q. So in this decomposition, you define the root of unity action on this piece, which depends on the fractional part of this P. But what's important is that we require this one previously defined as now defined on a complex space. We require this to be defined on over R. It's defined on E. Okay, so this is really just motivated by the requirement of this finite monodromic condition. So you pull back by a power, then you get a constant structure on Gn, and this gives you a natural action of monodromic. then for the example, also motivated by the example here, is that in this setting, the essential new object beside this classical one is this exponential A1. So this is the gamma motive. Okay, so we define this E M the cohomology, this A1 minus S M. Okay, so this is simple that probably you can take the wrong realization, and also you have this basic realization. I will write down the elements. Okay, so first, okay, so the wrong part. Okay, so this is really probably better to write this one. Be more consistent. So this is generated by the following elements. I call this omega j, which is the class of Sj minus 1 ds. Okay, A1. And with respect to this decomposition, it lies in the 5 degree 1 minus j over m. J over m. Okay. So what is the T action? This is just this is just induced by the geometric one T x S by roots of unity times S. Okay, so because on this space and this function, there's no homomorphism by this roots of unity. Okay, so it turns out that this generated eigenspace for this loop action. Okay, and j is from 1 to n minus 1, so the dimension is n minus 1. And why we call this gamma motives? That is actually we can also have a baby homology. Okay, then we go to the dual version, so we can compute the periods easily. So this baby part is the so-called rapid decay homology. So it's A1 SM. So here I need to, because I want to have a pairing between the one cohomology with the other one, so I need to change the coefficient to be the dual to. Okay, so this is dual to each other. So we have a natural pairing on the coefficient. Okay, and what is this? So this is called the rapid decay homology. Okay, and it consists of certain complex with coefficient. Okay, coefficient is the solution shift for this connection, which is the analytic solution. So this connection E plus E S to the power n. Okay, but this is just the C Q times exponential minus S to the power n. Okay. Okay, so what are they? So somehow the definition requires you to, the rapid decay condition means that you can have an infinite trend that start on the finite place toward infinity, but you require that the direction to infinity is such that the coefficient decay rapidly. And you can easily see that in this, under this requirement, the space. Okay, so this is equal to summation AI times n to the I times R plus. Okay, you rotate your positive real line such that along this straight line, the exponential function decay rapidly. Okay, times this increased by your coefficient. Okay, and so toward infinity, if we decay rapidly, we regard this as a no boundary. So the all this has boundary at origin, and if you want to make it as a cycle, you require that the sum of the coefficient is 0. Okay, and one has the period pairing. And this one you expect, so you have this differential form, and you have this chain. So you just integrate this chain, so there's a summation of this function, this coefficient, times your differential form. Okay? And then this is just equal to zeta n times j n gamma j n. Okay, so the appearance of this motive somehow is just the gamma function evaluated at the frictional basis. So I want to regard this as somehow a Tate twist. So usually the Tate twist has periods by I to some power, and then I want to add this into your consideration, so we can consider more arithmetic applications. Okay. I want to emphasize that, and also go back to your question. In general, if you consider this a general function on a variety, it won't be finite monodromic. Okay. One justification is that if it's finite monodromic, then the round cohomology with this irregular Hodge filtration I defined to you actually satisfy this conjugate condition. But in general, if you have another general function here, the exponential twisted the round cohomology do not have this property. So this is really a very strong condition. So I would say that if the final goal is to understand the motivic or arithmetic properties of this exponential twisted sheet, we are still very far away. Okay, so okay, and then you can slightly generate this to the prototype example. So in general, if you have for the function looks like s to the power n as u. Okay, you also have this this geometric monodromic action. And this gives a finite group action on the round cohomology and so on. And this with the irregular Hodge filtration I cannot define is actually satisfying this condition. Or you can compute in other way, that is you decompose your cohomology into pieces like this. So here you already know how to define. So this comes from m. Okay, so this is just a constant with the classical Hodge filtration. Okay, so you know how to define the irregular Hodge filtration in this special case. Okay, so let's move on. Really, Hanakian viewpoint. So let's look at the real case. Okay, so let's look at how to characterize real finite monodromic Hodge structure. Okay, so I want to describe this in a more geometric representation, theoretical point of view. So for classical real Hodge structure, you know that each real Hodge structure corresponding to a group representation for the group, so-called the leading torus. Okay, so what is that? You need to have a bi-grading. So this usually known by this S, boldface S. This is just a GM, so the C star action. But you regard this as a defined over R. Okay, so this is called the grade restriction. So more precisely, if you look at this character group, okay, so which is the the C of group homomorphisms of this S to 3n, it has two characters generators, which is just C to C, and then add the complex complication, and then the Daw group action for the field R is you interchange this. Okay. So this is so each action gives you by grading. So this character acts on dpq is z to the power minus p and z bar to the power minus q. But you want to have this conjugate condition, and this is when you do the conjugation, you need to interchange these two characters. Okay, so this starts looks more like a motivic setting, okay, compared to the classical one. So I want to define for the extended finite monodromic torus. Okay, so what happens is that now we have by grading by real numbers, and we can consider this. So let me write this one. So this is what I want to define. Okay, extended in torus at finite level in M. We have a finite cover. Okay, and this map is to the power M. Okay. So I want to say that even though you have this by grading, so if you say are integers. Okay, so you can forget about this denominator in the sense that you consider just the m's power cover of this torus, and then you regard this representation of this one. Okay, but you require that the conjugation, the sum of this. So for this finite monodromic one, you require that the sum is an integer. Okay, which means that what is this one? Okay, so this is subgroup inside here, and the character group is AC plus EC bar. Okay, in this character group is S prime, which is because we have m's cover, this is 1 minus 1 over m of this character group. You require the sum of these coefficients to be integer. Although in the beginning you can be rational numbers. Okay, so this pair take care of the condition that the sum of this by index, although each one is a rational number, but the sum is an integer. Okay, so, and then you define this as field to be the inverse of this union of this m. Okay, so the first nice property is that each finite monodromic Hodge structure is just a representation of this extended the torus. Okay, the first is field version is the fundamental group. The group of the dynamic category finite monodromic structure over R. And you can calculate this structure, so we have a select sequence, which is this as field is the extension of the classical one by just roots in the monodromy action. Okay, so it corresponds if you have a canonical generator here, and whenever you have a representation of this as field, this one just corresponds to a monodromy action. the usefulness of this the lead torus is that you can study the symmetry of finite monodromic Hodge structures. In the sense that whenever you have a finite monodromic Hodge structure, maybe not over R, let's say, so if you have a V, finite monodromic Hodge structure, and you can define so-called Mumford-Tate group. Okay, and T, E would be the smallest group, the group in B, okay, which preserve the Hodge structure, okay, such that if you consider the R points, it contains this is the condition, the image for this group. Excellent. Okay, so this is just the analog of the classical definition. Really, just the set. Okay, but you just replace your group, the leading torus, by this extended one. And then you can define what is called the CM rational finite monodromic Hodge structure. That is, if this Mumford-Tate group is commutative. Rational finite monodromic Hodge structure B is called CMI. Its Mumford-Tate group is commutative. Okay, and the basic example is that the gamma motives are CM type. Okay, so this EM is the CM type. So why is that? Because if you consider the T as regardless as T modular, okay, then this over as a vector space, this has dimension n-1 with the T action over M, and the all roots are just appear. The eigenvalue of this T consists of all nth roots of unity except one. Okay, because we describe this explicitly. So somehow this one and this will isomorphic to U, this T action, and this T satisfies and 1 is 0. Okay, so we know that actually this is isomorphic to field extension AN, n greater than 1, n divided m, where this AN is the cyclotron field extension. And the Mumford-Tate group will respect this each element is so-called like a Hodge cycle. So you preserve this all the automorphisms. Okay, so it turns out that the Mumford-Tate group will lies in the the product of the multiplicative is a group, which implies that the Mumford-Tate group is commutative. All right, so we can limit the extended in torus to the case of CM finite monodromic Hodge structure. Classically, CM Hodge structure is categorized by a representation of so-called Serre group. Okay, and then we can define the extended Serre group. Okay, so group, it turns out to be all functions from our Z locally constant. Okay, so which means it's vector through a finite extension such that F applied to any sigma plus F sigma composed with a complex conjugation is constant, independent of sigma. Okay, so this is just if you are familiar with the CM theory, so this just corresponds to all possible so-called CM type. Okay, but and then for this we can define this extended version. Okay, let me just denote it by S. Let me just write down the results. Stay with you. Okay, so this is in XS. So now you allow the value of this function to be rational numbers, but the condition is that not just if you apply the conjugation, this should be constant. You also need to have sigma minus cyclotonic field, cyclotonic character is in the okay, where this is a cyclotonic character. Okay, it adds just on the rules of unity. Okay, so the theorem we have is that first this S2 is actually the fundamental group of the category of the finite monodromic Hodge structure over Q, where the longer K group is the median. Moreover, actually, one has moreover, okay, so this one is actually is generated by a classical CM Hodge structure. So of course we have a classical one and just the gamma model. Yeah. Okay, so there's a good news that I also after the talk in the afternoon, we can see that if you were in the finite monodromic case, you can. It's really like a classical motivic consideration. That is, I talked about this Hodge part. Then actually in the afternoon you will see there's a Galois with the second part, also for this finite monodromic one, even though it's not classical. But you need to allow the twist of this gamma motive. And in the afternoon this will correspond to the twist by Gauss sum. But there's a bad news. That is, if you consider this irregular Hodge structures, if you restrict to yourself to this finite monodromic and abelian one, the CN type, then it seems like there's no hope to have extra elements besides the classical ones and this gamma twist. So somehow, as I said, that this is really a strong condition for this finite monodromic. Okay, so the other one is that you also have a exact sequence. One, the hash is S still S1. Okay, again, this generator corresponding to the monodromic case. Okay, so the proof actually use this, as I mentioned, that we can treat this gamma motive as a generalization of takes twist. So let me just write one sentence to explain how to prove this one. So ingredient is that if we consider this finite monodromic Hodge structure over Q, and if you consider this classical Hodge structure over Q, so let me write a Z hat here, means that you have a finite group action. Cyclic group action. And there's a map between these two, that is, I can define this B flat, which is B tensor B, monodromic invariance part, where this, right here, where this E is the limit of this EM. Okay, we just consider all the possible denominators for the Hodge decomposition, and then this E is the dual version. Dual. Okay, so what happens is that then if you apply twice, so for this, so the monodromic invariance one just corresponding to the classical Hodge structure. So if you take the invariance ones, this gives you classical ones. But there's a finite group action which is induced by T times 1. Okay? But if you do this operation twice, you will have a V, and you take out this T invariance part. So which means that if you have a CM finite monodromic Hodge structure, if you allow to twist this gamma motif, actually you have a classical ones, but it's still of CM type. So this explains that why this category is just generated by the classical Hodge structure, and also this EM. Okay. So yeah, let me stop here.
Is there any relation between this and the classical ODE finite
okay. So
and I mean, of course, there are two cases. If it's either regular singular or it could be irregular. But if you see irregular, the model is very weak. You know, because you need to compose the cells. So, but I'm just asking, if I just have an order differential equation,
yes, usually. So if the so the result is that if the somehow for example, one relation could be that if you only have if the connection on P1 is so somehow rigid, then you only need to require that the monodromic action has eigenvalue root unity. So and then substitute that there exists irregular Hodge structure on this connection, unique up to shift the Hodge equation. And if you consider the connection only have two singular points, 0 and infinity, and finite monodromic like this, then it but I mean, abstractly, you can, if there's a Q structure and so on, then you can certainly define this to be there's a finite monodromic Hodge structure such that if you take the differential D module part, this gives you the one you like abstractly. But there's would be a very weak information because for these finite monodromic ones, you just require that the pullback by a finite power, cyclic power is a constant. So in this sense, yeah, if you have a differential equation set by this equation, then abstractly you can put the finite monodromic Hodge structure up on it. But somehow probably is not very interesting.
Any other questions? Comments? That's actually Jeng Daw Yu. So also the organizers pretty help this.
好像各一张。
please.
So 你要从这边照是不是？
都可以啊，都可以。是这边一张，楼下一张，2张。
OK，所以我们应该站在这边照。
好。
So result of this last slide.